Okay, so last section was some discrete distributions, and we didn't actually find a whole lot to do with them. You can use them, binomial, the hypergeometric, and the Poisson. People use them in the real world, but they're used for very specific things, and you just don't run into them very often. More likely to run into is something called the normal distribution. And the normal distribution is the kind of fundamental distribution of what we use, and it is a continuous distribution. So you may remember at the beginning of class we talked about a guy named R.A. Fisher who invented a lot of stuff. He didn't invent the normal distribution, but he's the one that kind of figured out how we use it in the modern world. So you sometimes hear it as a Gaussian distribution. That's because this guy named Gauss is credited at least as the inventor of this distribution. In the old days, people referred to it as the error distribution, and they did that because in life it seems like things don't necessarily follow the normal distribution, but the errors we make do. And what I mean by that is, think about throwing a dart at a dartboard, and you keep throwing the dart at the dartboard, you throw it at the bullseye, but you don't hit the bullseye. If we take your darts, let's say you throw 100 darts at the dartboard, and we take all your darts and we average them. We don't just take them compared to the bullseye. We figure out where the average is of all the darts you threw, the mean. And then we measure how much error you had of each dart away from the mean. Your error in your darts would tend to follow this normal distribution. The dart throws might not, but the error will. And that turns out to be highly useful in statistics. A lot of times in statistics we analyze the errors we make, not the actual outcomes, but the errors. And the errors tell us a whole lot more sometimes than the actual thing. So this is the fundamental distribution of what we call parametric statistics, and it's the basis for most of what we do. So again, we looked at three discrete distributions. Remember, a discrete distribution is one where the numbers are apart from each other and there's no number in between them. So a hypergeometric, it might be 3 people in line or 4 people, or 3 people, picking 3 or 4 in the lottery. The number's 3 or 4 and there's no 3.5. A binomial, we're looking at, spinning that roulette wheel 35 times, and we're looking at, getting 27 blacks out of 35 spins. And the Poisson, we're looking at 3 people in line or 4 people in line or 5 people in line. There's not 3.5 people in line. The continuous distributions are essentially infinite, and any number can show up in those. And there's 4 of them that we're going to talk about by the time we're done with class: the normal, the t, the chi-square, and the f. The simplest thing to remember about that is those are all based on the normal. So the t is a modified normal. The chi-square comes out of the normal. The f comes out of the normal. Those 3 are all related to the normal distribution. So when we're using those other distributions, it's a normal distribution that something has been done to modify. Okay? And again, continuous distributions means if there's the number 3 and the number 4, there's something in between. There's a number. If there's a number 3 and 3.5, there's a number in between. These are infinite distributions where there's always something in between. So, what are the characteristics of the normal distribution? Well, the first characteristic is that it's bell-shaped, and I should have put the drawing of one on here, but I didn't for you. So I'll draw you a freehand one, and that's not a very good one, but it has this bell curve. You hear about teachers who say a grade on a bell curve, and that means 2.5% A's, 2.5% F's, 13% B's, 13% D's, and everybody else gets a C. That would be a bell curve. There are scientists who believe that intelligence of human beings follows this bell shape, and there's, kind of the same percentage of very smart people as the same percentage of not very smart people, and most people are in that lump in the middle. The normal distribution is infinitely long, both plus and minus, and we know that the real world is never infinitely long, both plus or minus, but it turns out that the error that's created by the fact that the real world is not infinitely long is a very small error. So we know when we do something with statistics that the actual error involved is a little bit bigger than we say it is a lot of times, but it's not big enough that we need to worry about it, and you'll understand why hopefully before this is over. The normal distribution is symmetric. That means it's the same on both sides. So if I take the high point and draw a line down, this side and this side should look exactly the same, symmetric. This side and this side are the same. And then this line I drew, which is at the highest point, is the mean of this distribution. It's also the median and the mode. So we don't have to worry about using the mean or median or mode. They're all the same. Okay? So the trick to this is, the funny part is, that probability is measured by the area under the curve. So here's my normal distribution. And let's say that this is how long it takes me to get to work, and on average it takes me 20 minutes. I want to know how often it takes me between 18 minutes and 20 minutes. Well, the answer would be I'd have to calculate the area right here. This block between 18 and 20, that area under this curve, that's the probability of probability of me driving to work and it taking between 18 and 20 minutes. The trick here is that this is a curvy shape. It's not a straight line, and that makes the calculation require calculus. And you're saying, oh my goodness, I don't have calculus. How would I calculate that? And the answer is, we don't expect you to. We all use tables of the normal distribution, which someone has already calculated everything for us. So we'll get to that, but don't worry about it. But there's a problem in doing the math because this is not a straight line, but you need to calculate the space under here. Now the funny part of this mathematically is that the probability of any one point is 0. So if I were to say to you, what's the probability of it taking exactly 20 minutes for me to get to work? The answer is 0. But if I add up an infinite number of zeros, I get 1. The whole curve has a probability of 1. Each point in it has a probability of 0. And again, if you're saying, how can I add up an infinite number of zeros and get the number 1? Go ask Isaac Newton. It's all about calculus. But it works. Okay? So in the normal distribution, we never ask the question, what's the probability of 18 minutes? We ask the question of what's the probability of being between 18 and 20 or 18 and 1802 or some two values. We say what's the chance of being between these two values, because the probability of any one value is always 0. There is an equation that defines the normal distribution, and again, we don't need to know it and we don't want to know it, but there's only two variables in it, and those two variables are the mean and standard deviation of our data. So once we know the mean and standard deviation of our data, assuming, and you know what problem you get into if you assume, but assuming that our data follow the normal distribution, we can, at least mathematicians can, plug the mean and standard deviation into this equation and solve all our problems, get the answers to the probabilities. So again, the normal distribution looks like this. The mean's in the middle. It has this bell shape. It's symmetric. This side looks like that side, and if I have 2 points on there, A and B, that's a B. The probability of being between A and B is the area under the curve in here. That block tells me the probability of being between A and B. Okay? So, the shape. We talked about the fact there's these things called skewness and kurtosis. This has 0 skewness. It is symmetric. It's identical on both sides. So if we were to calculate this variable called skewness, or we would have Excel actually calculate it, we wouldn't calculate it, but if we would have Excel tell us what the skewness is, we would come up with the number 0. And we have this thing called kurtosis, which measures how flat or steep something is, but that's compared to this. Okay? So if we say it's flat, that means it's flatter than a normal distribution. And if we say it's peaked, that means it's more peaky than a normal distribution. Okay? Flat, we have a name for that. Flat means platykurtic, and we have 2 platypuses over here to help us remember that. Platykurtic. So the relatively flat line, this one, would be platycurtic. The pointy one, the Washington Monument-shaped one, is leptocurtic. So next time you're in Washington, D.C., if you want to impress your friends, you can say, hey, did you know the Washington Monument is a leptocurtic? And then if it's just right, it's mesocurtic. So it's kind of Goldilocks. The first bowl was too flat. The second bowl was too peaked. But the third bowl was just right. So mesocurtic is the normal distribution. Okay? All right. So, again, we don't want to do the math. We want a table. We only have one table. There's an infinite number of normal distributions, but we only have one table. And that table is for what we call the standard normal distribution. Standard. When you see the word standard in statistics, you can just substitute average, and that works. So the standard deviation is the average deviation. The standard normal distribution is the average normal distribution. It has a mean of 0 and a standard deviation of 1. And what we do in problems involving the normal distribution is we transform the normal distribution that we have into a standard normal, and then we look up the answer to our problem in this normal table, which is actually the table of the standard normal distribution. So we have this thing called a z-score. The z-score is x, which is our point, minus mu, the mean, which is x minus mu. On average, the mu is equal to x. So x minus mu is going to subtract out to 0. And then these x minus mu's, they create the standard deviation. So the standard deviation divided by the standard deviation, when you divide a number by itself, you get 1. So this minus this on average is going to be 0. And this divided by that on average is going to be 1. So this z-score transforms our numbers into a set of numbers that have a mean of 0 and a standard deviation of 1. And then we can go look the answer up on the table. Okay. So we need to find the probability. We have a standard deviation. And now I'm doing something which you may or may not believe, and which statisticians argue about. But there are people who believe that people's IQs have a mean of 100 and a standard deviation of 10. So, assuming we believe that, and that they're normally distributed, and maybe they are, maybe they're not, maybe they're all cultural, and maybe there's all kinds of other things going on here, but that's not my point. So we've got a mean of 100 and a standard deviation of 10. What percentage of the population has an IQ between 100 and 120? Well, to calculate that, we would need to find the area under this curve. What we're going to do is convert this 100 into 0. We're going to convert this 120 into something else. And from that, we're going to figure out what the probability is by looking it up in the table. So we need to find the z. And to do that, we started off with 100 and 120. So we're going to come over here. We're going to take 120 minus 100. And we're going to divide by 10. Again, where do we get those numbers? The mean is 100. The standard deviation is 10. So we're going to take this 120 right here. Z equals 120 minus 100 divided by 10. And that's 2. 2 what? 2 standard deviations. That's 2 times sigma, the standard deviation. So again, we can come over here and plot this. This is always 0. The middle is always 0. So here's 2. So now we've converted this into a standard normal distribution. Okay? It's a standard normal distribution. And we have a 0 and a 2. And we're going to go look that 2 up in our table. Okay, so here we are. Here's our table. Standard normal distribution and Z. And we go look up. Down the side here, we have 0, 0.1, 0.2, 0.3, 0.4, 0.5, all the way down to 3. Across, you see we have 0.00, 0.001, 0.002, 0.02. So 2, this number right here, that number right there, goes with 0.00, 2.00, and it's just 00 up here, so that's 2. So 0.4772, remember that. If we wanted to look up 2.02, we'd take 2 from here, we'd take 0.02 from up here, and we'd get that number. That number is 2.02. Okay, we'll try that again later, and hopefully in a second it will make more sense to us. So again, we looked up the number 2 in the table. We looked up that number in the table, and it said 4772. That means this probability here is 0.4772. Okay, so 47.72%. Okay, so 47.72% of the normal distribution is between 0 and 2, or in this case, the percent of people who have IQs between 100 and 120 should be 47.72%. Now, more fun in the world. This curve is symmetric. This line splits it in half. So from here to infinity, and that's a movie line, right, is 50%. And from here to infinity this way is 50%. So if this is 4772, what's that part? This part, by the way, is called the tail. How much is in the tail? Well, if that's 4772, the tail has to be 0228. And why? Because that number and that number have to add up to 0.500. Okay? And that means I can come over here and go to 80, which is minus 2, and this is 0.4772, and this is 0.0228, and that plus that plus that plus that adds up to 1. Isn't that beautiful? You're like, oh my goodness. Don't worry. Pretty quick, you'll be laughing at your friends next semester who are having trouble with this because it's so simple. Okay? So, what's the chance of a probability less than 120? Well, again, we would calculate the z. The z is 2. That means this part is 4772. Less than 2 means from here all the way to minus infinity. We don't have to worry about that because from here over is 0.5. It's half. Right? Half the distribution's over here, half it's over here. So what's the probability of less than 120? Is 4772 plus, that's a plus, 0.5 equals 0.9772. And yes, my handwriting sucks, especially on the computer when I'm writing with my mouse. Okay, so 97.72% of people have IQs below 120. So there's a society for smart people called Mensa, and to get into Mensa, you have to be above 120 because they believe that IQs have a mean of 100 and a standard deviation of 10. And you have to have an IQ above 120 because that's 2 standard deviations from above the mean. And essentially, they're letting 2.28% of the people into their club. They say top 2%, but really it's 2.28 because they're using 2 standard deviations. And they're excluding the 0.9772. Okay, so again, the probability of between 100 and 120 is 0.4772. So the probability of less than 120 is 0.9772. And the probability of greater than 120 is 0.0228. And the probability of exactly 120 is 0. All right, so again, the probability of being between 80 and 120, because we're symmetric, if this over here is 0.4772, this over here is going to be 0.4772, and we add those up and we get 9,544, because plus 2 and minus 2 in the table work out the same. We ignore the minus sign when we go look a number up in a table. Okay? So, what's the chance of being between 110 and 120? That means between here and here. Now we have a problem because our table is measuring between 0 and somewhere. So what we're going to do is get 2 numbers. We're going to get this number, and then we're going to get this number, and the difference between them, we're going to subtract the 2 numbers. The difference between them is this part here in the middle. So we're going to look up, we're going to calculate, this is 100, right? This is 110, and this is 120. So we're going to take 120 minus 100 divided by 10, that's 2. We're going to take 110 minus 100 divided by 10, that's 1. We can't subtract the 2 from the 1 and get 1. What we're going to do is go look these up in the table. So we're going to jump here. We looked up 2 already. When we look up 2, we get 0.4772. And we look at 1, we get 0.3413. Okay. So, again, what are we going to do? We're going to get a number here. From here to here, all of that is 4,772. From here to here, that is 3,413. So we're going to take 477, subtract 3,413. Okay, so that's 5,931. It's 1,359. So this area in here, that blob, is 1,359. How are we going to get this? We're going to practice. There's an old bad joke, yes? Tourist in New York going to a concert at Carnegie Hall is lost. Stops a cab driver, says, "How do I get to Carnegie Hall?" Cab driver says, "Practice, practice, practice." In Vegas, that would be kid walking down the street, dribbling his basketball, and he asks some adult, "How do I get to the Thomas and Mack?" And the adult says, "Practice." How are you going to get good at this? You're going to practice. Okay, let's try another one. So, ignore that 2 that's right there. Let's say I want to know what's the probability of being between 100 and 115.5. Well, now I'm going to do the math. I'm going to take 115, so I want all of this, right? I want all of this. and this is 115.5. I'm going to check 115.5 minus 100, divide by 10, and I get 1.55. So this is 0, and this is not 2. I'm evil. This is 1.55. Now all I do is go get my table, and here's 1.5, right? Here's 1.5, but I need 1.55. And where's that second 5 coming from? It's here. So I come down to that number right there. That number is 1.55. So it's 0.4394. I come back here, and I say, okay. That's 4, 3, 9, 4. And that's not 2, that's 1.55. So that's between IQs of 100 and 115.5. What percent of the population has IQs between 100 and 115.5? The answer is 43.94%. Okay? All right, so go to Carnegie Hall. Go practice.